This is ECE 343, Signals and Systems. This will be the second part of Chapter 4. Last time we introduced the bilateral Laplace transform. The bilateral Laplace transform of the signal x of t, which we call cap x of s is just a frequency variable, is computed by taking the integral, right, of the signal x of t multiplied by the exponential e to the minus st, and the limits of integration go over all time, so minus infinity to infinity. This is the most general form of the Laplace transform, and last time we saw that it was necessary to specify this thing called the region of convergence. The region of convergence is those values of s for which cap x of s exists or converges. We knew that regions of convergence helped us decide whether the original time domain signal was a right-sided signal or a left-sided signal. So it helps us establish a unique transform pair. If you do not include the region of convergence, you wouldn't know just looking at cap x of s whether the terms, the time domain terms, corresponded to right-sided signals or left-sided signals. So it really is important in the bilateral Laplace transform case to specify that region of convergence so you know whether individual terms that make up the time domain signal are right-sided in nature or left-sided in nature. There is a special case of the bilateral Laplace transform called the unilateral Laplace transform. We'll designate this with a script L subscripted with a U. So unilateral Laplace transform of some signal x of t. We're going to still call it a cap x of s, and it's still an integral of x of t times e to the minus st. Nothing different there. It's just now we're only going to integrate from 0 to infinity. We're only going to integrate over non-negative time. So really what the unilateral Laplace transform does is it assumes that signals are causal. Because it assumes that signals are causal, right, the region of convergence would have to be a right-sided region of convergence. We know then that all unilateral transforms are going to have regions of convergence pointing off to the right. And as a result, you probably don't have to specify explicitly what the region of convergence is. We can infer it knowing that the underlying signals, because of that causality assumption, were right-sided. There would be no penalty for specifying a region of convergence for the unilateral transform. It just isn't totally necessary because it is implied because of the underlying assumption that unilateral transforms are working with causal signals. Unilateral Laplace transforms are particularly useful to solve constant coefficient linear differential equations when we have non-zero initial conditions to incorporate into those solutions. We looked at the time domain solution of differential equations back in Chapter 2. We knew that you could do things like zero input and zero state responses, two separate pieces. When we get to this Laplace transform solution, I think that we'll all agree that the overall mechanism of solving those equations becomes greatly simplified. We'll do more in demonstrating how to use the unilateral Laplace transform to solve differential equations once we get through some properties. Before we get to properties, let's just make a brief statement about how we carry out the inverse Laplace transform, so the inverse operation of a Laplace transform. We had shown the inverse Laplace transform equation in the previous lecture, and we noted that that had, if you were going to do it in a strict mathematical sense, it had an integration with respect to a complex variable s. And we really don't have in this class the mathematical prerequisites to carry that out directly. So instead, when we do the inverse Laplace transform, which we'll designate just with the script L raised to the minus 1, so an inverse Laplace transform. If it was a unilateral version, you just had the little u subscript in there. If we're going to do an inverse Laplace transform, we're just going to do a partial fraction expansion, maybe use some properties, and then consult a table of common Laplace transform pairs. We've already seen a couple of Laplace transform pairs. So for example, we looked at a signal like this. We looked at a signal that maybe was e to the minus t u of t. And when we transformed that in our previous lecture, we saw that went over 1 over s plus 1, and it had a region of convergence that said something like the real part of s was greater than, minus 1, where that root was at, something like that. So this would be a typical kind of table element. It would tell us something about a common time domain signal in this particular case, like a decaying exponential, and what its transform is. If we could identify, through a partial fraction expansion, some terms like this, that had a region of convergence in the form of something to the right of the root, right? Then we would know that the underlying time domain signal was something like that decaying exponential. So I think the best way to maybe show this is through an example. I'm going to take a pretty simple example. I'm going to look at a transform cap x sub a, the first case of s, is a purely rational function, 1 over s minus 1 times s minus 2. And I'm going to give it a region of convergence that's the real part of s being greater than 2. If you take a look at this particular rational function for x of s, right? We see that there are two factored roots in the denominator. So there are two values of s which make that cap x go off to infinity. If s equals 1, right, we would get 1 minus 1 in the denominator. That would be 0 in the denominator. That whole entire expression then would blow up to infinity. Same sort of case if we let s equaling 2. Those two values of s that make this transform cap x of s go to infinity are called the poles of the system. We had mentioned before that we could plot out those poles, right, in the complex frequency plane, the complex S plane, just a Cartesian plane. So we're going to go ahead and identify those two values of 1 and 2 using an X. That X, right, is just our indicator for a system or a signal pole, something like that. So I'm going to go ahead and put them there at 1 and 2. And based on our previous lecture, we knew that poles, because they're the thing that make this transform blow up, right, cannot be included in the region of convergence. So I put some dotted lines there just to show that those are boundaries. We can't intersect those pole locations. Okay, so we have this this strictly proper rational function. I want to break it into simpler pieces just so I can consult some tables and be able to invert each one of these individual pieces. So take your favorite partial fraction expansion technique. I use the Heaviside cover-up method in this case, and we're just going to re-express xa of s, right, as a sum of lower order rational functions. So if you go ahead and do that, you're going to have a term for the s minus 1, you're going to have a term for the s minus 2. The coefficients in the numerator are found again by your favorite method, so I just use the method of residues, also called the Heaviside cover-up method, and you can easily find out that those coefficients are minus 1 and 1. You can cross multiply here, get a common denominator, and see that you get the original transfer function, or the original expression 1 over s minus 1, s minus 2. So I now have what? I have a simpler expression for my transform. xa of s now, instead of showing it as this kind of high degree of complexity rational function, I'm now showing it as a sum of some simple pieces. And we've seen the transforms that involve something like a 1 over s minus 1 or a 1 over s minus 2. That was this first thing that we look back over here. A 1 over s plus 1, for example, gave me e to the minus t. A 1 over s minus 1 is going to give me an e to the t kind of term. So we can just consult our tables, and there's a table of these in the book. Right now, these are consistent with the ones that we've done last time. We know that this first one is going to have an e to the t type of behavior, and the second one, the one corresponding to 1 over s minus 2, is going to correspond to an e to the 2t behavior. What I need to figure out, though, is whether they are right-sided or left-sided. And so again, I'm going to take a look at my original region of convergence. The region of convergence here, right, said that the real part of S is greater than 2. This region of convergence is the convergence area for both of these. When you look at those original, right, the original waveforms in there, we know that pole at 2, for example, would have two possibilities. It could either have a region of convergence to the right, or it could have one to the left. This idea of real part of S greater than 2 is to the right of that guy, right? And in the same way, if I look at the root at 1, it would have a region of convergence that could either point to the right of it or to the left of it. And clearly, S greater than, the real part of S greater than 2 is pointing to the right of that one as well. So I've colored in kind of a light green here the area that is the region of convergence. That's all S values whose real part is greater than 2. And we see that that region of convergence is to the right of both the pole at 1 and the pole at 2. Because the region of convergence is to the right of those guys, these two terms must invert transform to right-sided signals. Now we have everything that we need in order to complete the invert transform. We knew it was a form e to the minus t, or e to the t, or an e to the 2t, just because of the root locations at 1 and 2. And now, because of the location of the region of convergence relative to those roots, I know that they're going to be causal u of t's. And then we just multiply by those coefficients. So I'm going to get a minus e to the t ut plus e to the 2t ut as being my time domain signal xa of t, two right-sided components. As a second example, we're going to take that same exact rational function. I'm going to call this xb of s, and it's still 1 over s minus 1, s minus 2, except for now I'm going to look at a different region of convergence. I'm going to look at a region of convergence that is the real part of s squeezed between 2 and 1. If I re-look at where those roots were, right, we knew that there was a root at 1 and there was a root at 2. Taking that real part of S between 1 and 2 gives me that thin yellow strip, right? That thin yellow strip between 1 and 2. If you look at the root 1, right, if I take a look at that value of the root at 1, right, that strip is to the right of it. So the region of convergence for that pole at 1 is to the right of the pole. If I take a look at the region of convergence relative to the second pole at 2, right, the strip is to the left of it. That region of convergence is going to suggest a time domain signal that is left-sided rather than right-sided. So we still do the same PFE, we still do the same partial fraction expansion. XB of S is still going to be minus 1 over S minus 1 plus 1 over S minus 2. We could have gotten that from our same work before. But now when I look at that term minus 1 over S minus 1, that's the one that has the root at 1, right? The thing that is going to be dictating that particular guy is going to be its, and I think I might have got something a little bit, no, I've got something kind of goofy in here. So let's go ahead and fix this. I think I've got my logic back in here. We can correct that though. So let's make sure I get this right. So if I look at this first one, right, either minus 1 over S minus 1 or 1 over S minus 2. Let's take the minus 1 over S minus 1. That's this root at 1. The region of convergence is to the right of that, right? And so that is the real part of S greater than 1. So I can take that guy and connect those guys together. And because it's right, we know that this guy is going to be right-sided, right? So this is going to be a right-sided component in there. If I look at the second one, that's really being dictated by this guy over here. That's the real part of S less than 2, right? And because it's less than, when I connect it to the corresponding root in there, this is going to be a left-sided. This is going to be a left-sided root. So when I go through and I carry this guy out, and boy, I got this double wrong twice in here. So let's go ahead and fix all of it. We're going to definitely correct this guy. Mistakes do happen. That's why it's good to check your work, right? So the first one in here, in fact, let's just erase that whole thing and just do it as we go along. The first one is a right-sided term. And we know that right-sided term, right? The right-sided term is going to be just like what we had before. We had already computed out what a minus 1 over S minus 1 does when it was a right-sided term. That was this piece right in here. So I can just copy that right down, right? I'm going to get, in this case, a minus e to the minus t u of t in there, something along those lines. The other one, though, is a 1 over S minus 2, and it's left-sided. Now, if you look at the tables, a 1 over S minus 2, when it's left-sided, the root's at 2, so that's going to be an e to the 2t term, right? Because it was left-sided, I'm going to get a u of minus t term, but you'll also find out that there was another minus sign. So there's an extra minus sign in that case of left-sided components. You could also consult our first lecture on this. You would have seen that there was a sign difference in the first two examples that we did. So you do have to consult the tables, but we end up getting now a pair of signals here, right? One of these guys is going to be right-sided, and so we can go ahead and identify that if we wanted to, right? So we take a look here, right? This guy, I'm going to do this in a different color. This was my right-sided, that's my right-sided piece, and the other one was left-sided. And the way I knew that they were right or left-sided was just by looking at where the region of convergence was, right, relative to the underlying pole, right, the underlying root that created those terms. Okay, so you can do this for however many poles there is in a signal. The basic idea is you have a rational function. You use a partial fraction expansion to bring it up into a sum of a bunch of pieces, and then you look at where the region of convergence is relative to each of those pieces to decide whether you use a right-sided or left-sided component. For the remainder of the lecture here, we're going to talk about some Laplace transform properties. These Laplace transform properties help us get insight into signals and systems, and they also just considerably make things simpler as far as carrying out computations and calculations. We're going to mostly consider properties here that are associated with the unilateral Laplace transform. There are also a series or a host of properties, the same corresponding properties for the bilateral Laplace transform, and almost always they're really quite similar. So you'll find that the bilateral and unilateral Laplace transform properties are similar. I think the book does a little bit of a muddled job as far as showing these properties and maybe not always being 100% explicit as to saying whether they are using the unilateral case or the bilateral case. So I really would encourage you to take a look at the formula sheet that's on the class website, right? And it's the one you also get to use on the next test, and it provides a side-by-side comparison of the bilateral Laplace transform and unilateral Laplace transform properties. So you can see exactly how they're the same and how they might differ. For the most part, as we go through in this lecture part, I'm going to deal with the more complicated, or what tend to be the more complicated cases, which is the unilateral. So we're going to focus primarily here on the unilateral transform. To get us started on this, let's just start out with a preliminary. We're going to go ahead and say that there's a signal x1 of t, and it has a known transform x1 of s, and there's going to be a signal x2 of t, and it has its transform x2 of s. So those are going to be given as knowns, and then we're going to work through a series of properties. We'd actually shown this last time in our previous lecture. I'm just going to restate it for completeness here. Any linear combination of signals in the time domain, when you transform them, gives you the same linear combination of signals in the transform domain. So a x1 of t plus b x2 of t has a Laplace transform that is a cap x1 of s plus b cap x2 of s. So same combination in both time and transform domain. These are very easy to prove. That particular one is. How could you prove it? You would just sit there and you would take this expression and you would plug it into the Laplace transform formula, and you would go to work. And because a Laplace transform is based on integration, and we know integration is a linear operator, the result pops out pretty easy. I won't prove this particular one because it is so easy. I'll spend most of my time when I want to do a proof here, proving some of the stuff that is not quite so obvious. The time shift is one of those cases, so we'll do some proofs here a little more detailed. The time shift property says what? It says if I take a signal and I shift it in time, you don't have to recompute its transform. You can take the original transform for x, right? So little x of t has a transform cap x of s. And if I shift that time domain signal, so I get x of t minus cap minus t sub naught, we end up just getting our original transform cap x of s, and it's going to get multiplied by an exponential that depends on what? It's going to depend on the amount of shift. That's why you see that e to the minus s t naught. So if I shift by t naught, what happens in the transform domain is you're just going to get multiplication by an exponential, where that exponential's argument, right, depends on the amount of shift. So shift in time, multiplication by an exponential in the transform domain. I will say that this one is one of those cases where that would be always true if we were talking a bilateral Laplace transform. For a unilateral, we have to be just a tiny bit careful, and I'll try to give some intuition on this. This is perfectly okay. It's perfectly fine. We definitely get this if the parameter t naught is greater than 0, corresponding to a delay. But we might find that there are some problems, right, if t naught is less than 0 for an advance. And I'll provide some intuition on that in a second. Let's first prove, right, that at least for the t naught greater than 0 case, the delay case, that this property is indeed what it says it is. That delaying in time just causes a multiplication by an exponential in the transform domain. So here's how I'm going to do it. I'm just going to go ahead and take, by definition, the Laplace transform of this modified signal, x of t minus t naught. So I'm going to look at what is the Laplace transform of this delayed signal. I know that the unilateral Laplace transform is an integral, right, that goes from 0 to infinity, and I just put in the signal and I weight it by e to the minus st. Okay, let's go ahead and let there be a change of variables. So I'm going to go ahead and let t prime equal t minus t naught. That tells me dt prime equals dt, and I can reestablish this integral because I had x of t minus t naught. T minus t naught was just t prime, so I'm going to get an x of t prime now. If I go ahead and look at e to the minus st, I would have to solve for t. That's not too hard to do, right? I can just take that original expression that I had that related t and t naught. I could take this guy and I could rewrite it for t. That's going to be t equaling t prime plus t naught. And I could go ahead and plug that guy into my expression there where it said e to the minus st. Now we know t is t prime plus t naught. So what do I get? I get e to the minus s times t prime plus t naught. We know dt is just dt prime, right? Same thing there. So I can replace dt with dt prime. And then I do have to figure out what happens to the limits of integration. If x is 0, which was what originally we had in our lower limit. I plug that value 0 into my original expression here, right? So I'm going to get t prime equals 0 minus t naught. That's going to give me minus t naught. So I see a little change on that limit of integration. The upper limit, right? If I put t equaling infinity, infinity minus some finite shift is still going to be infinity. So my upper limit remains at infinity, something like that. Okay, so I have a slightly alternate expression here. Why did I do this? Because I'm trying to work towards the known result, or what I believe to be the result, which is that I should have an x of s, right? So I want to have an integral with just an x of t in it. I want to be working on that. So a couple things that I can note here. I know that x of t, because I was talking about a unilateral transform, the assumption is that signal is causal. So I know what? I know that x of t, right, is 0 for any values of the argument less than 0. If I look at this limit of integration, right, it goes from minus t0 was a positive number, that's what caused it to be a delay, minus t0 to infinity. I can break that integral then from minus t0 to 0 plus then 0 to an infinity. But for minus t0 to 0, because x of t0 is 0, right, in that region, I'm just going to get an integral of 0, and all that's going to disappear, so I never even see that. So really, even though that the limits did appear to change to minus t0 to infinity, it doesn't really add much because there just is a bunch of 0 in there. I'm still left with that x of t prime, and then if I take a look at that original whoops, that's not where I wanted to go. If I take a look at that original exponential function, I have e to the sum of some terms, and I know I can write something raised to a sum power as a product of terms. So in this particular case, if I break that out, I get an e to the minus st prime, and I'm going to get it multiplied by e to the minus st naught. E to the minus st naught, right, is not a function of the variable of integration. It can be pulled outside, so I pull that guy outside. Integral of 0 was 0, so I didn't have to worry about that. And what's left, I have an integral from 0 to infinity of a signal times e to the minus st prime dt prime. That's just by definition the Laplace transform of x, so I'm going to know that that's x of s, and that finishes out the proof. We have shown that the Laplace transform of this delayed signal, x of t minus t naught, right, is just this complex exponential weighting my original transform. Okay, so these get kind of tedious. We probably don't want to do them every single time, but they really aren't that difficult. You usually just plug in on one side of the equation and you start using a set of logical steps some logical steps in order to demonstrate that the end result is indeed true. I would like to make a few seconds here, though, to talk about a graphical argument, why the case for an advance when t0 is less than 0 can cause problems, but that the case t0 greater than 0, which is a delay, does not. So for me to do that, let's look at this first signal I have over here. I have a signal x of t that I call my igloo function. So it kind of looks like an igloo. You see this green waveform, and it sort of looks like an igloo. I've drawn it so that it is green for all positive time and it's red for all negative time. I do that purely to emphasize where the unilateral transform is going to be doing its stuff, right? Unilateral Laplace transform, right, has an assumption of causality. It's only integrating from 0 to infinity, right? So when I go out and I figure out what is x of s, it's going to involve an integral from 0 to infinity. So it's integrating that entire igloo function in order to get this cap x of s. So cap x of s is just an alternate representation. It's a frequency domain representation of that igloo function. Now, if I take the case t0 greater than 0 and look at x of t minus t0, that's a delay. That shifts the igloo over to the right, right? And so I've got a picture of that there as well, and we still see there's that green igloo sitting out there. It's just been moved over to the right. If you look at where the unilateral transform is going to be integrating that function, right? It's for all non-negative time, so all the green stuff, and it ignores all the stuff to the left of the origin, right? So all the red stuff is ignored. That still looks like an igloo, right? It's still an igloo. So I would expect my transform domain to have some dependence on something that says, hey, I'm an igloo. That's the cap x of s. The remaining term, the e to the minus st naught, is really just transform speak for shift that guy, right? So cap x of s in this case was I'm an igloo, and e to the minus st naught was I'm an igloo shifted over to the right. What happens in the other case? When I have x of t minus t naught for t naught less than 0, that's an advance. So I'm shifting it to the left. I shift that igloo off to the left, and I've shown it for a particular case t naught here, where the entrance to the igloo is kept, but most of the bulk of the igloo has been shifted off to the left of the origin. That's shown in red. Okay? When I unilateral transform this, right? When I unilateral transform this guy, it is going to ignore all of that stuff. It's going to ignore the bulk of the igloo. It is only going to worry about the stuff sitting out here to the right. That just looks like a little entrance, right? It looks like a little rectangle. It doesn't look like an igloo at all. Me shifting this to the left and doing the unilateral transform, the shifting to the left shifted content away from where the unilateral transform looks. It is no longer an igloo, and you would not expect there to be, right, some transform domain expression that would involve x of s, which is just the transform representation for something that's an igloo. So hopefully this gives a little bit of insight. If you have a waveform and you shift it to the right, you're never going to change the underlying character of that. So we would expect the transform to still share a lot of that same information. If you shift to the left, there's a great danger. It doesn't always happen, but it almost always happens that when you shift it to the left, when you do an advance operation, you end up losing some pieces of that signal, and that's going to fundamentally change its nature, and that's going to fundamentally change the nature of the transform. So you don't get that nice, easy property piece. There is another property in here. It's a frequency shift property. This is a dual, if you will. We'll talk more about duality. We looked at in the previous property that a shift in time was multiplication by an exponential in the S domain. Here we're taking a look at what happens when I shift the frequency variable. So if I take cap x of s minus some value s naught, what do we find in the time domain? Well, it's just going to be x of t times an exponential, e to the s naught t. You'll notice it has a sign difference than what we saw in the previous one. This is not a hard one to prove. I'll let you look at that on yourself. But it does illustrate this underlying kind of behavior of Laplace transforms that are very typical, that what tends to go in one direction, going from the time to the frequency domain, usually has something pretty similar going from the frequency back to the time domain. So in property 2, when we talked to time shift, right, we said a shift in time gave us multiplication by an exponential in frequency, and this shift in frequency property says if I shift in frequency, I get multiplication by an exponential in time. Pretty neat. Kind of helps us remember these guys. Time differentiation is one of the most important properties, so we'll spend a little more time on this. And it basically says something like this. If I have a time derivative of a signal, right, and I Laplace transform it, I'm going to get s times x of s, and then maybe some initial condition dependence, okay? For the unilateral Laplace transform, you're going to see those initial condition terms. If you take a look at the time differentiation property for the bilateral transform, you won't see those initial condition term dependence, so it's an easier property. And this really highlights why we use the unilateral transform to try to solve differential equations with initial conditions. Think about that. If they have initial conditions, we're saying we already know what's happened up to time 0. We're only interested in what's going forward of that. The initial conditions reflect everything that happened before, right? And it's really going forward of 0 that we're interested. That's that kind of causal assumption. That's why we use the unilateral transform. And this unilateral transform will explicitly incorporate these initial conditions in there. So the property says if I time differentiate, that derivative, which used to get kind of tangled, our variable x got stuck to that ddt, now it becomes something that can be multiplicatively separated, right? X of s is multiplied by s. What does s say? That's just our frequency domain, s domain. That's our derivative in time, right? In frequency domain is just represented by an s. An s squared would mean a second derivative. An s to the 10th would mean a 10th derivative, a 10th order derivative. So this s times cap x of s would be interpreted as a time domain expression as being take the derivative of little x of t. And then we see explicit, which is nice, this explicit dependence on the initial condition. Let's go ahead and prove this guy. I'm going to prove it in the standard way. I'm going to go ahead and take what I'm trying to work with, ddt of x of t, and I'm going to go ahead and plug it into the unilateral Laplace transforms a definition. Unilateral transform says I integrate from 0 to infinity of that signal, in this case ddt xt, multiplied by an exponential e to the minus st dt. I'm going to use integration by parts. Everybody should be aware of that in calculus. So an integral of u dv equals uv minus integral v du. And if I just set u equal e to the minus st, and my dv is being that signal x prime basically times the differential element dt, I can go ahead and do my integration by parts here. I'm not going to do all the steps. You can check this out yourself. What we end up getting is uv, which is going to be x of t e to the minus st, evaluated on my integration limits, 0 minus to infinity. And then I'm going to subtract, right? And I'm going to integrate the vdu. And if you take a look at that vdu product, it's minus s x of t e to the minus st dt in there, something along those lines. Let's concentrate on the first part of that. I've colored that red just so we can focus on that. If I look at that first term, x of t e to the minus st, and I think about evaluating it at the upper limit at infinity, I'm going to have something like x infinity e to the minus s infinity, and we have to figure out what the heck to do with that. Here's the basic strategy we can take here. We already acknowledged that x of t, right? X of t had a Laplace transform that was x of s. That was our given assumptions, right? So we know x of t is Laplace transformable. Because it is Laplace transformable, the product x of t e to the minus st, that's the argument of the Laplace transform, right, is integrable in the region of convergence for that transform. And the only way that that happens is if that term tends to 0 as t goes off to infinity. So we can make an argument, because x of t is Laplace transformable, that that first term evaluates to 0. If this is something that bothers you, we don't have to get too focused on it. This is a proof. I would like you to understand it, but it's not 100% crucial for you to probably agonize over every single detail. Try to work your way through it, but it's just part of showing that this stuff is true. What am I left with then? I evaluate at the lower limit, so I go minus, evaluate that expression at the lower limit. I'm going to have x of 0 e to the minus s times 0. E to the 0 is just going to be 1, so I'm just going to get little x of 0. That's the initial condition stuff, right? If I look at what's on the right-hand side, so if I look at those right-hand side terms, I see that there is a variable s, right? But we're integrating with respect to t, so I can pull that s outside, right? So I get that s outside. Furthermore, there was a negative sign both inside and outside of the integral. A minus times a minus is a plus, so this whole thing is going to become a plus. And I look at what's left on the inside. It's an integral over those standard limits, 0 to infinity, of x of t e to the minus st dt. That is just by definition x of s. And then I get my final result, that the Laplace transform of a differentiated signal, right, x prime of t, or ddt of x of t, or x dot of t, however you want to notate it, the Laplace transform of the first derivative of the signal is just x times the transform of the original signal, non-differentiated, x of s, right, minus that initial condition. We can generalize this, and so this generalized formula is just no fun to prove. We know the general style of this. The rest of it's just kind of tedious. If I take an nth order derivative, what do I get? I get a polynomial multiplier, s to the n. S to the n you can interpret as meaning the time domain signal was differentiated n times. And which thing was differentiated? Well, the signal x. So I'm going to get s to the n x of s. The rest of this stuff is all of the initial conditions. So this is all the initial condition stuff, right? That's the initial condition. And that really came out of it being unilateral. So we will see this. We see with the Laplace unilateral, not with just the regular old Laplace. You aren't going to see that same kind of an explicit dependence on initial conditions. If I broke this out term by term, if you just kind of wanted to get the sense of it, that Laplace transform, unilateral Laplace transform then of the nth order derivative is an s to the n x of s, right? And then I start breaking out these terms here in the sum, and I get something like the n minus 1th derivative of x evaluated at 0, and then I'm going to subtract s times the next order derivative down, so the n minus 2nd derivative evaluated to 0, all the way down to I'm going to have a polynomial s to the n minus 1 times just the signal by itself. So if you look at that, that depends on NICs. What are those NICs looking like? You see stuff like there's an x of 0, right? You're going to have x prime at 0, right? And keep going on up in there, and you're going to go all the way up to x of n minus 1 at 0. These are our standard ways of expressing our initial conditions. We saw that before when we were solving differential equations, right? Just reversed ordered here. Time integration property. We can make short work of this because we just don't use it a lot. Almost always we deal with the differential form of our equations. It's just more convenient, so it's easier to work with the differentiation property than the time integration. But time integration basically says, hey, if I integrate and if I do it over positive time, if I integrate a signal, right, I'm going to get that signal's transform, but I'm going to get just 1 over s instead of s. So s means differentiate, right? S to the minus 1 or 1 over s means integrate, something like that. Again, these can be proved. I'm not going to prove this particular one. If I went ahead and allowed the integration to go minus infinity to t, well, you still would get the same result that comes out of the 0 to t part of the integration, and then there's the rest of the stuff. The proof is in the book here. Again, I don't think it adds a lot of insight to go through that whole proof. I will say that this serves a lot like an initial condition. It's kind of a different form of an initial condition, or it reflects the state of everything that happened to the signal before time t equaling 0. We won't make huge use of the time integration property. Scaling, beautiful property, love this one. So if I take a signal x of t, and I multiply the independent variable by a, so we know this is a time scaling operation. Let's go ahead and just leave a be positive for now. You can take a look at the book as to what happens when a is also negative when we have a reflection. Go ahead and unilateral. Actually, it wouldn't make sense to reflect in this case. You can reflect for the bilateral, but not the unilateral. Why? If you reflect, right, what was a causal signal before would become non-causal, and boy, that just wouldn't make any sense at all for a unilateral transform. So yeah, let's go ahead and do the scaling using a positive constant. So I'm going to take x and I'm going to time scale it, a times t, right? What happens in the transform domain? I'm going to get 1 over a x of s by a. So if I scale t by a, right, I'm going to scale s by the reciprocal of a, by 1 over a then. So this introduces something that we oftentimes refer to the scaling property as the reciprocal scaling property of the Laplace transform. I think there's a really intuitive way to look at this as well. I think it should become something that seems pretty obvious. I'm going to just show some waveforms that I think are things that we're all familiar with. Let's take a look at a signal x of t that is just a sinusoid. So I'm going to draw a cosine here, and I'm going to go ahead and let this guy have a period being equal to like 1 second. So if I look at the distance for peak to peak on this guy, I'm going to let it be 1 second. So we went ahead and said, hey, the period there is 1. We know that that's a 1 hertz waveform, right? So the frequency of that guy is 1 hertz, something along those lines. Now, if I time scale that, if I do x of 2t, right, what is that? That's a compression operation. So I multiplied the independent variable t by the factor 2, and everything in the time domain got squeezed, right? It got squeezed and went smaller. So now the t, right, is equal to a half. So I compressed things in time, right? When I multiplied t by 2, I made the time dimension get compressed. But what happened in frequency? When you have a shorter period, right, that means a higher frequency. So the frequency didn't compress, the frequency doubled, right, because it has to do twice as much in the same amount of time. So it went from a 1 hertz waveform to a 2 hertz waveform. I think this makes it reasonably obvious why when we compress in time, we have to expand in frequency, reciprocal spreading, right? Or if we expanded in time, we would have to compress in frequency. Another property, we're getting pretty close to being done. There's a convolution property. This is going to be one that I think most of us are going to really appreciate. Convolution is a difficult, time-intensive operation in the time domain. We notated that before as x1 convolved with x2, for example. If you unilateral transform that guy, though, that convolution operation becomes multiplication. So convolution becomes multiplication. Again, this is not difficult to prove. It is tedious. I won't do it. You can look at the proof on book or online. You just basically take that convolution integral, you stuff it in the integral that is the unilateral transform, and you go to town to demonstrate that it's equal to a product of two known transforms. What does this also mean? We've been spending a lot of time, if you look back at chapter 2 when we were solving differential equations, we did stuff like the zero state response was equal to what? It was an input convolved with the unit impulse response. That convolution wasn't fun. So what would happen if we Laplace transform that guy? We could solve for the zero state response as a product of the transform of x, right, times the transform of the unit impulse response. We're going to call that h of s. By the way, that's that same h of s, that multiplier constant, if you sent an everlasting exponential through our system. We can solve for that h of s as just being the transform of my zero state output, okay, over input x of s, okay? Since our impulse response and that transfer function, that h of s, are a Laplace transform pair, we know that we could invert transform that guy to get me back my unit impulse response. So the unit impulse response, a different way of getting it, is the inverse Laplace transform of the zero state response over an input, something like that. Think about how you did h of t in the previous chapters. H of t had something like some delta function, and there was some coefficient out there, like maybe b0, and then you had a PD acting on y tilde of t, u of t. You had to find that zero input like kind of y tilde. You had to find the coefficients for that using some special initial conditions. It was just a big pain. Here, we can do it just through a very simple operation. We take a ratio of output to input in the transform domain and then invert transform it. Part of the reason I avoided the proofs previously for the time domain operations is because almost no one computes or determines an impulse response using time domain expressions. Almost everybody does it using these transform domain expressions because it's just easier. We'll do more of that when we get to the part of solving differential equations using the Laplace transform. That'll start next lecture. Let's do an example though, of showing how this particular a convolution property might be put into practice. It might help us out. So I'm going to take an example here where I have an output generated as a convolution of two signals, okay? So I have a decaying exponential that's been shifted over to the right one. So this is an exponential that starts at 1. If I was going to just kind of make a quick sketch of that guy, right? It's going to look something like that. And then I'm going to be convolving that with another decaying exponential. And that one's just a little bit different. It's got a little more aggressive, and it's also going to delay a little bit more. This one delayed out to 1. This one's delaying out to 2, and this one's going to be a sharper decay because it's e to the minus 2 times something. So causal exponentials, one is delayed by 1, one is delayed by 2, one's a little bit more aggressive decay rate than the other, and I'd like to convolve these guys. If I was going to do this in the time domain, right, we'd have to go through the 3-step method. You'd have to plot one guy, you'd have to plot the flip and shifted of the other guy, you'd have to identify regions, you'd have to compute for those regions, and then you'd have to go through and simplify all that mathematics. Take a look at what happens here in the transform domain. E to the minus t minus 1, u of t minus 1. That looks like what? If I do something like this, whoops, that's not a very good marker for this one. Let's do it like this. If I look at e to the minus t, u of t, and I delay, right, by 1, I get e to the minus t minus 1, u of t minus 1. Okay, so I have already seen the transform of something like e to the minus t ut. That's actually in my transform books. That's 1 over transform tables. That's 1 over s plus 1. And I know what it means to delay a signal by 1 because of our properties, right? We know a delay in time is multiplication by an exponential. E to the minus, whatever the delay was, 1 in this case, times s. So I'm going to get e to the minus s. So through simple properties and tables, right, I can easily take the transform of that first argument, right? E to the minus quantity t minus 1, u of t minus 1 transforms to e to the minus s times 1 over s plus 1. I can do the same sort of stuff for this second term, right? That's going to be e to the minus 2s because it was delayed by 2. And it had a root at minus 2, so it's not 1 over s plus 1, but it's 1 over s plus 2, something along those lines. So far, really not a big investment here to find the transforms. The real magic, the real goodness here, right, happens right here in the middle. That convolution operator, right, we know when something is convolved in the time domain, it becomes just plain old multiplication in the frequency domain. So instead of having to worry about convolution, I don't have to do one bit of convolution here. I had to take the forward transform, and I'm going to have to take the inverse transform, but all I have to do now is multiply some stuff together. Let's go ahead and think about how to multiply that. I see an e to the minus s and I see an e to the minus 2s. So if I take that first one and I multiply it by that second one and combine terms, I get an e to the minus 3s. What do I know that means? E to the minus 3s times something means whatever the inverse transform of that something is, right? We're just going to delay it by 3. So I'm going to leave this guy out front because I know that means delay by 3, something like that. And then I just need to figure out what it is that I have to be delaying. So I've shown that in a bit of a light blue there. I've got a rational function, 1 over s plus 1 times s plus 2. We see that there's 2 roots in there. I'm going to go ahead and do a partial fraction expansion, right, so that I can get simpler terms, stuff that I can easily find in my table of Laplace transform pairs. So if you go ahead and do that, use the Heaviside cover-up method and method of residues, clearing fractions, whatever you want to do, you get something like this, 1 over s plus 1 plus minus 1 over s minus 2. So partial fraction expansion on just that part that was blue. Let me make a little caution here. I see in some cases where people are trying to do their partial fraction expansion and they accidentally try to take a partial expansion of the whole thing. Remember, partial fraction expansions are only working on strictly proper rational functions. This e to the minus 3s out front is definitely not a rational function, right? And so it would ruin our underlying function for which partial fraction expansions apply. Partial fraction expansion as a technique takes rational functions. E to the minus 3s is not going to give us that rational function requirement. So leave it outside. If you put it on the inside, you're going to mess everything up. So I definitely leave it out on the outside, and it's going to be easy to handle, right? Because I know what it means. It just means delay. And I'm left then with this partial fraction expansion, which is a 1 over s plus 1, right? And a minus 1 over s minus 2. Because I was doing a unilateral transform, right? In this particular case, I was looking at a unilateral transform. I had two causal signals. Here was a causal signal, here was a causal signal, right? Two causal signals, unilateral transforms, totally appropriate. You don't see me actually giving things like a region of convergence. That doesn't mean it doesn't exist. It doesn't mean that we don't have a region of convergence. And in fact, we can show what that region of convergence looks like. That region of convergence is going to be something like the following. I'm going to look at it in the S-plane. I see one of these guys has a root at what? -1. So that's the first term. The other one has a root at, that should have been a plus, at -2. So I'm going to get this root at -2, something like that. Because they were both right-sided signals, right? The region of convergence is going to point to the right of each one of those and can't include a pole in there, or the actual denominator root of this guy. So I know this first term has to have a region convergence and points off to the right there because it was a right-sided signal to begin with. Same thing with this guy over here. So there is an underlying region of convergence, even though we don't always report it for this case of unilateral transforms. And it's this part of the S-plane that is to the right of sigma, or it's to the right of this point -1. So sigma, or the real part of S, I'm going to just do it as the real part of S, right, is greater than, in this case, -1. This was -1 here, this was -2 there. So that really is the region of convergence. If you wrote it down, there's no problem, okay? It is there, but it's usually not reported because unilateral transforms assume everything is right-sided. Okay, we could infer it from this. We could infer it just by taking a look at this guy, plotting its two roots, and saying, oh, I can't keep this guy, and I can't keep this guy, and I know it has to be to the right because it was a unilateral transform. That gives me this region of convergence over there. Same sort of thing. So I'm going to invert this with tables and properties, and I should be able to finish this guy out. So this first term, 1 over s plus 1, what does it invert transform to? We've already seen that. That's an e to the minus tut. But then I have to do what? I have to delay it by 3. That's going to give me an e to the minus the delay, t minus 3, u of t minus 3. The other term in there, -1 over s plus 2, right? The -1 is going to give me this minus right here. And then I'm going to have a root at -2. That's going to be an e to the minus 2 tut. But it also is applied, or having this e to the minus 3s applying to it, or multiplying it, which means I've got to delay that one as well. So I'm going to get an e to the minus 2, not t, but t minus 3, u of t minus 3. And that's my final result. So you could go through the 3-step procedure, and when you get to a simplified answer, you would see that it matches this one exactly. That requires a whole bunch of kind of math. Or we can solve it using this Laplace-based mechanism. The Laplace method does have some steps that are a little different than what we saw in the time domain. You do have to take the forward transforms. You do have to take the inverse transforms. But usually that comes at a savings in overall effort, because we can replace what are sometimes really bad, horrible, awful, difficult to do convolutions with simple multiplications. Okay, 2 final properties and then we'll be done. There's something called an initial value theorem, and then there's also something called the final value theorem. The initial value theorem is I'm just going to state it here, and then we'll kind of talk a little bit about how we use it. It says that if the Laplace transform of a signal x of t and its first derivative exist, well, then I can determine, or there's a relationship between the initial value of the time domain function, little x at 0, right, can be gotten from my transform domain expression, cap x of s multiplied by s, in the limit as s goes to infinity, if the limit exists. Okay, so this seems kind of weird. It's mixing. Usually you don't see this kind of mixing. You usually don't see equations that involve, time domain expressions and transform domain S expressions, something along those lines. But in this particular case, it says I can get some time domain behavior, this little x at 0, from my transform domain expression, x of s, multiplied by s, looking at it as going s to infinity. Proof of this is not terribly informative. It's in the book if you'd like to look at it. Final value theorem is something very similar. Okay, it's very similar. It says that if the transform of x of t exists and the Laplace transform of the first order derivative exists, okay, then we can get this final value theorem, and it basically says that the last value of x, so x at infinity, little x, the time domain waveform, out at infinity, can be gotten from its transform domain expression, x of s, in the limit as s goes to 0. Okay, so as you look towards the point t equaling 0, you're going to be looking in the frequency domain as s goes out to infinity. And vice versa. If I'm looking for t equaling infinity, I'm going to be looking when s goes to 0. This is also conditioned on some mild conditions. It says the poles of s times x of s have to be in the left-half plane. All the proofs are in the book. How are we going to use these guys? The initial value theorem and final value theorems really are primarily useful as a quick error check. I'll give an example of that here in a second. If you go on and take like the controls class, you'll use more kind of interesting applications of the initial value theorem and the final value theorem. Let's go back to something that we knew. We saw a waveform before that looked something like this. We had what? An e to the minus t, u of t, and we know what that guy transformed to, right? That was a 1 over s plus 1, something like that. Now, does that signal's transform exist? Yes. And does its first derivative transform exist? Yes, it does. So let's go ahead and find out what this initial value theorem and final value theorem say. The initial value theorem says that x at 0, now we can explicitly get that in this case. What is x of 0? We're going to get e to the 0, that's just 1, times u of 0, which is 1. We know at t equaling 0, at t equaling, oh, that's not so great, at t equaling 0, let's try that again. At t equaling 0, we get a 1 on that guy, right? So we would have in this particular case, right, x of 0 is being 1. And then I want to look at that. So we're saying, is that guy equal to? We'll find out, right? Limit as s goes to infinity of s times x of s. So that's going to be s over s plus 1. So what is the limit as s goes to infinity of s over s plus 1? This is a limit as s goes to infinity of a rational function. In this case, the highest orders of s are the terms that dominate. So this is going to be the same. You can do a little review of calc to see this. This is the same as the limit as s goes to infinity of s by s, which is 1, by the way. Okay, and so we got 1 equals 1 as expected. Where might we use this? Suppose instead you had incorrectly, right, computed out the Laplace transform of e to the minus t ut, and you instead said it was something like 2 over s plus 1. Let's say you'd done that. If you took that 2 over s plus 1, multiplied it by s, that would be like a 2s over s plus 1. And you could look at the limit of that guy as s goes off to infinity. And you could find out in that case that's 2, which is not equal to 1, which you could easily tell as being the original initial value. In this way, because you got this conflicting value, you know to question that original transform that you took. 2 over s plus 1 is not giving me a consistent value. This isn't something you have to do all the time. Like I said, it's a diagnostic. It's a way of doing some error checking in some cases. You could do the same sort of stuff there for the final value if you wanted to. Next time, we're going to talk about solving differential equations using Laplace. So just a very quick recap of this one. We introduced this thing called the unilateral transform. We did talk about taking the inverse transform based on doing a partial fraction expansion and consulting region and convergence to know which table elements or table entries to use in that inverse transform. We can incorporate some properties in there to also simplify that inverse transform process. Then we looked at a bunch of transform properties, right? Those transform properties give us additional insight into these signals, and they give us a bunch of tools with which to solve problems efficiently. We're going to really see that next time. We're going to get much more out of this kind of esoteric kind of theory-based stuff, and we're going to start solving circuit problems, something that's much more tangible, something that just feels a lot more real. So that'll be next time.